GTC is where we talk about industry, science, computing, the present, and the future. This is the treasure of our company. Most people talk about the GPU. The GPU is important, but without a programming model that sits on top of it, and without dedication to that programming model, keeping it compatible over generations. We're now CUDA 13 coming up on CUDA 14. Hundreds of millions of GPUs running in every single computer, perfectly compatible. If we didn't do that, then developers wouldn't target this computing platform. If we didn't create these libraries, then developers wouldn't know how to use the algorithm and use the architecture to its fullest. One application after another. This is just a representative of 350 different libraries in our company, and each one of these libraries redesigned the algorithm necessary for accelerated computing. Each one of these libraries made it possible for all of the ecosystem partners to take advantage of accelerated computing, and each one of these libraries opened new markets for us. We have a lot of industries to cover today. I'm going to cover AI, 6G, quantum, models, enterprise computing, robotics, and factories. Let's get started. We have a big partnership with Nokia. Nokia is the second largest telecommunications maker in the world. It's a $3 trillion industry. Infrastructure is hundreds of billions of dollars. There are millions of base stations around the world. If we could partner, we could build on top of this incredible new technology, fundamentally based on accelerated computing and AI, and for the United States, for America to be at the center of the next revolution in 6G. So today we're announcing that NVIDIA has a new product line. It's called the NVIDIA ARC, the Aerial Radio Network Computer, Aerial RAN Computer, ARC. ARC is built from three fundamental new technologies: the Gray CPU, the Blackwell GPU, and our ConnectX, Mellanox ConnectX networking designed for this application. And all of that makes it possible for us to run this library, this CUDA-X library that I mentioned earlier called Aerial. Aerial is essentially a wireless communication system running on top of CUDA-X. We're gonna create, for the first time, a software-defined, programmable computer that's able to communicate wirelessly and do AI processing at the same time. This is completely revolutionary. We call it NVIDIA ARC. And Nokia is going to work with us to integrate our technology, rewrite their stack. This is a company with 7,000 fundamental, essential 5G patents. Hard to imagine any greater leader in telecommunications. So we're going to partner with Nokia. They're going to make NVIDIA ARC their future base station. So today we're announcing the NVQ-Link. NVQ-Link. And it's made possible by two things. Of course, this interconnect that does quantum computer control and calibration, quantum error correction, as well as connects two computers, the QPU and our GPU supercomputers, to do hybrid simulations. It is also completely scalable. It doesn't just do error correction for today's number of few qubits. It does error correction for tomorrow, where we're going to essentially scale up these quantum computers from the hundreds of qubits we have today to tens of thousands of qubits, hundreds of thousands of qubits in the future. So we now have an architecture that can do control, co-simulation, quantum error correction, and scale into that future. The industry support has been incredible. Between the invention of CUDA-Q, remember, CUDA was designed for GPU, CPU, accelerated computing. Basically using both processors to use the right tool to do the right job. Now, CUDA-Q has been extended beyond CUDA so that we could support QPU and have the two processors, QPU and the GPU, work and have computation move back and forth within just a few microseconds. The essential latency to be able to cooperate with the quantum computer. So now CUDA-Q is such an incredible breakthrough adopted by so many different developers. But in this new world, there needs to be a computer that understands context all the time. It can't pre-compute that. Because every time you use the computer for AI, every time you ask the AI to do something, the context is different. So it has to process all of that information. Environmental, for example, in the case of a self-driving car, it has to process the context of the car. Context processing. What is the instruction you're asking the AI to do? Then it's got to go and break down the problem step by step, reason about it, and come up with a plan and execute it. Every single one at that step requires enormous number of tokens to be generated, which is the reason why we need a new type of system, and I call it an AI factory. It's an AI factory for sure. It's unlike a data center of the past. It's an AI factory because this factory produces one thing. Unlike the data centers of the past that does everything, stores files for all of us, runs all kinds of different applications. You could use that data center like you can use your computer for all kinds of applications. You could use it to play a game one day. You could use it to browse the web. You could use it, to do your accounting. And so that is a computer of the past, a universal general purpose computer. The computer I'm talking about here is a factory. It runs basically one thing. It runs AI, and its purpose is designed to produce tokens that are as valuable as possible, meaning they have to be smart. And you want to produce these tokens at incredible rates because when you ask an AI for something, you would like it to respond. And notice, during peak hours, these AIs are now responding slower and slower because it's got a lot of work to do for a lot of people. NVIDIA is the only company in the world today that literally starts from a blank sheet of paper and can think about new fundamental architecture, computer architecture, new chips, new systems, new software, new model architecture, and new applications all at the same time. So many of the people in this room are here because you're different parts of that layer, different parts of that stack and working with NVIDIA. We fundamentally re-architect everything from the ground up. And then, because AI is such a large problem, we scale it up. We created a whole computer, a computer for the first time that has scaled up into an entire rack. That's one computer, one GPU. And then we scale it out by inventing a new AI Ethernet technology we call Spectrum-X Ethernet. Everybody will say Ethernet's Ethernet. Ethernet's hardly Ethernet. Ethernet, Spectrum-X Ethernet, is designed for AI performance, and it's the reason why it's so successful. And even that's not big enough. We'll fill this entire room of AI supercomputers and GPUs. That's still not big enough because the number of applications and the number of users for AI is continuing to grow exponentially, and we connect multiple of these data centers together, and we call that scale across, Spectrum XGS. Gigascale, Spectrum X Gigascale, XGS. By doing so, we do co-design at such an enormous level, such an extreme level, that the performance benefits are shocking. Not 50% better each generation, not 25% better each generation, but much, much more. This is the most extreme co-designed computer we've ever made, and quite frankly, made in modern times. Since the IBM System 360, I don't think a computer has been ground up, reinvented like this ever. So NVLink 72, if we were to create one giant chip, one giant GPU, this is what it would look like. This is the level of wafer scale processing we would have to do. It's incredible. All of these chips are now put into one giant rack. This one giant rack makes all of these chips work together as one. This is our third generation NVLink 72 rack scale computer. Third generation, GB200 was the first one. All of our partners around the world, I know how hard you guys worked. It was insanely hard. It was insanely hard to do. Second generation, so much smoother. And this generation, look at this, completely cableless. Completely cableless. And this is all back in the lab now. This is the next generation Rubin. While we're shipping GB300s, we're preparing Rubin to be in production, this time next year, maybe slightly earlier. And so every single year, we are going to come up with the most extreme co-design system so that we can keep driving up performance and keep driving down the token generation cost. Look at this. This is just an incredibly beautiful computer. Now, 100 times 100 of those, let's see, 100 of those would be like 25 of these racks, all replaced by this one thing. One Vera Rubin. Okay, so this is the compute tray, and this is Vera Rubin super chip. Okay, and this is the compute tray. This up right here. It's incredibly easy to install. Just flip these things open, shove it in. Even I could do it. Okay, and this is the Vera Rubin compute tray. If you decide you wanted to add a special processor, we've added another processor. It's called a context processor because the amount of context that we give AIs are larger and larger. We wanted to read a whole bunch of PDFs before it answered a question. We wanted to read a whole bunch of archive papers, watch a whole bunch of videos. Go learn all this before you answer a question for me. All of that context processing could be added. And so you see on the bottom, 8 ConnectX-9 new Super NICs. You have CPXs, 8 of them. You have Bluefield 4, this new data processor, 2 Vera CPUs, and 4 Rubin packages, or 8 Rubin GPUs. Ladies and gentlemen, thank you for joining us today, and thank you for allowing me to bring Thank you for allowing us to bring GTC to Washington, D.C. We're going to do it hopefully every year. And thank you all for your service and making America great again. Thank you.